Hi everyone. So today we will be going to the presentation of a project titled ARIS. ARIS stands for Autonomous Robotic Inspection and Surveillance System. This project focuses on developing an intelligent robotic system which is capable of autonomously navigating indoor environment and performing infrastructure inspection tasks. Our team members are Princely D'Souza, Sahaj Kapoor, Mohammad Mahir, and we are under the guidance of Dr. Vaishak Srikumar, and we are from Manipal Academy of Higher Education. Today, I will explain the motivation behind the project, the technologies that we used, working methodology, simulation results, and future scope of ARIS. So, coming to the introduction part, infrastructure monitoring is an important part of maintaining safety and operational efficiency in large institutions like universities, hospitals, and office buildings. So, traditionally, inspections are done manually by maintenance staff. However, manual inspections have several limitations. It requires significant human effort. It's time consuming. Some defects may go unnoticed. Hazardous areas can be difficult to inspect safely. So, in order to solve these issues, we developed ARIS, which stands for Autonomous Robotic Inspection and Surveillance System. So, ARIS is an intelligent mobile robot designed to navigate autonomously through corridors, monitor infrastructural conditions, detect faults such as structural cracks, water leakages, spillages, and faulty light systems. The main goal is to provide continuous and reliable monitoring inside the Mahidubai campus corridors. This system combines robotics, artificial intelligence, computer vision, autonomous navigation, and sensor fusions into one integrated inspection platform. So the main problem statement that we are trying to solve, like said earlier, in large institutions, manual inspection creates several operation challenges. First, the inspection are highly time consuming. Second, the human inspection is prone to error. Third, the inspecting ceilings or elevator regions safety can be difficult. So because of these challenges, there's a strong need for an automatic robotic solution that can continuously monitor infrastructure with higher efficiency and accuracy. This motivated the development of a project ARIS. So the objective of a project is mainly divided into two: primary objective and technical objective. The primary objective is to develop an autonomous inspection robot capable of operating in indoor environments. The robot should detect structural cracks on walls and ceilings, water leakages and spillages, faulty light systems. And another important objective is enabling real-time monitoring and reporting to reduce dependence on manual inspections. And coming to the technical part, we use to achieve this, we use RGB cameras with deep learning for defect detection, Jetson Nano for edge AI processing, ROS2 and Nav2 for autonomous navigations, sensor fusion techniques in improving detection accuracy. Overall aim of this project is to create a smart robotic platform that can perform inspection tasks efficiently and reliably. So before developing ARIS, we studied several previous research works related to the robot inspection and autonomous navigation. So these are the references that we used, and many existing systems have limitations such as high computational complexity, limited mobility, application-specific environments, lack of integrated and inspection capability. So our project attempts to combine navigation, AI-based inspection, environmental sensing into single scalable platform. So coming to the design system, so the system contains both hardware and software components. The hardware components, the main processing unit in Jets is the Jetson Nano, which handles AI and image processing tasks. The Arduino Mega acts as a control unit for sensor and motor interfacing. So the other components include RGB inspection camera, ultrasonic sensors for obstacle detections, moisture or thermal sensor for leak detection, motor drivers and DC motors, a three-wheel differential drive mechanism, and a robotic arm for interaction. So on the software side, we use ROS2 and NAV2 for navigation, OpenCV for image processing, deep learning algorithms for crack detection, sensor fusion algorithms for combining multiple sensor inputs. So the system architecture is as follows. The sensor and camera collects data and sends it to Jetson Nano, which processes the information, and AI makes the decision and alerts the action, and alert actions are generated. And this architecture allows the robot to operate autonomously while continuously monitoring the environment. So here we could see the electric circuit schematic for air system, which illustrates the integration of microcontrollers and ultrasonic sensors. So This shows how these microcontrollers and ultrasonic sensors are interconnected for obstacle detection and navigation controls. So the CAD model, this is the CAD model. The CAD model demonstrates the physical structure of the robot. The important design feature include dual-tier chassis design, top-mount inspection camera, sensor arrangement for 360-degree obstacle detection, compact body dimension suitable for corridor movements. The design ensures stability, efficient sensor placement, and ease of navigation in narrow indoor spaces. The methodology of ARIS consists of multiple stages. First one is initialization. The system performs self-checks on sensors and components. Second one is autonomous navigation. The robot navigates through the corridor using rows to and obstacle avoidance. Third one is data acquisition. RGB camera captures images continuously. And the fourth one is image processing. The OpenCV pre-processing using the So coming to the methodology of ARIS, which consists of multiple stages. The first one is initialization. The robot first performs a self-check of all the sensors and system components. And the second step is autonomous navigation. Using a ROS 2 navigation algorithms, the robot begins moving autonomously through the corridors while avoiding obstacles. Third step is data acquisition. The RGB camera continuously captures images of walls, ceilings, and floors. The fourth step, which is image processing, the captured images are processed using OpenCV pre-processing techniques. The deep learning model then analyzes the image to detect defects like cracks or damaged regions. Fifth step is sensor fusion. Sensor data from the ultrasonic and moisture sensor is combined with visual data to improve the reliability. And the sixth step is decision making. The AI system classifies whether defects are present or not. And the seventh step is alert generation. So, if a fault is detected, an image is captured, the location is stored, and alert is sent to the maintenance department. This creates an automated inspection pipeline. So, coming to the working principle begins with the in-system initialization and localization. The robot then starts autonomous patrol inside the corridor environments. So, as it moves, the camera continuously scans the surroundings. AI model analyzes the image in real time. Sensors monitors the environmental conditions. So different types of detections for crack detection, image and analysis is used for leak detection. Sensor data and visual confirmation are combined for faulty lights. Light intensity and analysis is performed. So whenever a defect is detected, the image is stored, the location is logged, and alert is generated. So after this one, the robot either continues the patrol or returns to the docking station depending on the battery status. This makes the system suitable for continuous monitoring applications. So simulation and testing. Before the physical implementation, we tested the robot in a gazebo simulation environment. The robot was modeled as a three-wheel differential drive platform. The simulation environment replicated the corridor layout of Mahi Dubai. The key features tested were obstacle avoidance, corridor navigation, turning at intersections, stable path following. Simulation stage was very important because it helps to reduce the hardware risk, lower development cost, allows safety testing of the algorithms. The robot also include a vertical adjustable camera mast, a forward-facing RGB camera, virtual sensing system for obstacle detection. So this help us validate the environment system for real-world deployment. So here we could see the simulated system represent a custom differential drive robot defined in SDA, which stands for Simulation Descriptive Format. It features a rectangular body measuring 0.5 meter by zero point 0.3 meter, driven by two independent rear wheel with passive caster wheel at the front. So to meet the structural health monitoring the requirement, the robot included an upper mast, like said earlier, equipped with a vertically adjustable camera carriage. This mechanism supports a facing forward RGB camera that can move up to zero point 0.4 meter along the mast. So coming to the navigation logic and control, the navigation system uses autonomous corridor navigation technique. The robot maintains equal distance from the wall using wall centering logic. So it can also identify intersections, open paths, and obstacles. The control system, the robot behaves in managed using finite state mechanism or FSM. The main state include forward motion, obstacle avoidance, and turning maneuvers. Smooth 90-degree turns are executed when intersections are detected. The perception system. So coming to the perspection system, the virtual sensing and raycasting techniques are used to accurate optical detections. So as a result, the robot demonstrates stable movement, smooth navigation, and collision-free operations. So coming to the the simulation results were highly successful. So the achievements that we got are navigated. The robot successfully navigated corridors autonomously, avoided obstacles efficiently, performed smooth turns, and planned efficient paths. The inspection system also showed reliable detection capability for cracks, leaks, and faulty lights. And some other major benefits include reduced inspection time, increased accuracy, early hazard identification, and improved maintenance efficiency. So, the overall results demonstrated that the ARS is a feasible and scalable smart inspection solution for educational campus. So, coming to the conclusion part, the ARIS, the Autonomous Robot Inspection Surveillance System project presents a smart and scalable approach toward the automated infrastructure monitoring within the educational environment such as Mahi Dubai. The proposed system combines autonomous robotics, AI-based image processing, environmental sensing, and real-time monitoring into one integrated platform. So at the current stage, the robot has been conceptually designed, simulated using Rosto and Gazebo, tested for navigation and obstacle avoidance. The results confirm that the platform can safely navigate indoor corridors and support future AI-based inspections. This project demonstrates the potential of robotics and AI in improving campus safety and maintenance efficiency. So the future works. There are several future improved plans for the area. So developing an full physical prototype. So there are several future improved plans for our project. Some of these are developing a full physical prototype, implementing complete SLAM-based navigation, improving AI accuracy for crack and leak detection, and adding wireless real-time alert system, and also creating a mobile or dashboard monitoring interface. Also enabling a complete campus mapping, adding voice interaction and guest assistance features, conducting real-world testing inside Mahi Dubai corridors. So this enhancement will make Aris more intelligent, interactive, and deployment ready. So this will be the end of it, and thank you everyone. We hope Aris can contribute towards a smarter and safer infrastructure monitoring system in the educational institutions.